In this video, we'll learn how to write net ionic equations. Net ionic equations are equations that show which ions are actually reacting in a solution. A few definitions before we start. First, we have a molecular equation. The molecular equation is a chemical equation that shows the complete neutral form of every compound in a reaction. This is the type of equation you guys are used to writing at this point. This type of equation shows our reactants and forming our products. The second type of equation we write is a complete ionic equation. The complete ionic equation is a chemical equation that shows all species as they are actually present in solution. So if we remember, in solution, ionic compounds break up into the corresponding ions. The complete ionic equation shows this. Then the net ionic equation is an equation that only shows the species that actually participate in a reaction. So this shows which ions are reacting to form our product and which ions are still just floating in the solution. So this equation shows which ions react to form our products and which ions will be floating in solution. First, before we start, we need to look at electrolytes. Electrolytes release ions when they're dissolved in solution. You've seen this before. This is called dissociation or ionization. If something is an electrolyte, it can conduct electricity. With electrolytes, those are our ions or ionic compounds, acids, or bases. Then we have our non-electrolytes. Non-electrolytes are substances that do not dissociate in water, and they also do not conduct electricity. These typically tend to be our molecular compounds, or when we have two nonmetals together in a compound. Once we know if something is an electrolyte or a non-electrolyte, we can break it apart a little further. It can be a strong electrolyte or a weak electrolyte. Strong electrolytes dissociate completely in water. They'll dissociate completely into their ions in water. They conduct electricity really well. Our strong electrolytes are ions, strong acids, and strong bases. Weak electrolytes do not dissociate completely into their ions in water, and they also do not conduct electricity that well, but they will conduct it a little bit. They typically tend to be your weak acids and weak bases. And just a reminder of what the strong acids and strong bases are. Strong acids are on our list here, such as HCl, HBr, HI, nitric acid, perchloric acid, and sulfuric acid. Strong bases are the hydroxides of group 1, such as lithium, sodium, potassium, rubidium, cesium, and also some of group 2, calcium hydroxide, strontium hydroxide, and barium hydroxide. If you have an acid or a base and it's not on this list, it is not a strong acid or base. Only the strong acids and bases are shown here. Everything else will be considered a weak acid or a weak base. Now that we know some of the definitions, let's start looking at our molecular equation. If I give you a molecular equation where I say you have potassium iodide reacts with lead nitrate, first you're going to have to predict the products. The first step is always write out the products. And so if we remember from our solubility rules, the iodides are insoluble when the counter ion is silver, mercury, or lead. And I see I have two ionic compounds here. Since I have two ionic compounds, I know I'm going to do a double displacement reaction. And with that double displacement reaction, if we remember the solubility rules, then I remember the iodide is insoluble when the counter ion is silver, mercury, or lead. So then I can write my products as lead 2 iodide plus 2 potassium nitrate. Since the iodide is insoluble, it gets an S for solid. So the first step is to always write a correct, balanced molecular equation. Once we write our correct balanced molecular equation, we can start to split apart all the ions. Because we know that potassium iodide does not exist as potassium iodide together like this in solution. Same thing with the lead nitrate. It does not exist as one entity like this in solution. So instead, we want to break apart the ions that are aqueous and strong electrolytes. So once we split apart all of the aqueous, strong electrolytes, we end up with an equation that looks like what's shown up here. This is a much more accurate reflection of what's found in our reaction mixture. And I want to emphasize that it's only the strong electrolytes that dissociate. If it's a weak electrolyte or non-electrolyte, do not break it apart. You write it in its molecular form. Same thing if it's a solid, a liquid, or a gas. Do not break apart solids, liquids, or gases. We can see our lead 2 iodide, that stays together because it's a solid. So even though it's an ionic compound, I cannot break it apart because it's a solid. It's going to be sitting on the bottom of my beaker as lead 2 iodide. Everything else here, the potassium, iodide, lead, and nitrate here, they can all be broken apart because they're all aqueous and all ionic compounds. Same thing with the potassium and the nitrate on the product side. Since it's aqueous and it's ionic, I can break it apart. So that means when you look at the complete ionic equation, I'm going to turn my molecular equation becomes the complete ionic equation. This is what the atoms and molecules look like in the actual reaction flask. You can see that the potassium iodide is not together. It gets split apart. The lead nitrate, same thing happens. The only thing I keep together is that lead 2 iodide. But so now when you guys are looking at our complete ionic equation, you can see there's a little bit of redundancy. I have 2 potassiums here, I have 2 potassiums here. It's kind of repetitive. So that's where the net ionic equation comes in. In the net ionic equation, we only list the ions which are not common on both sides. So that means we take our complete ionic equation and we cross out the ones that are on both sides. So here I have the potassium, here I have 2 potassium ions. Here I have 2 nitrates, here I have 2 nitrates. Since they're common on both sides and they're in the same phase, the same charge, so you can see they're absolutely identical, I can cross them out. So if I cross them out, since they don't do a reaction, they're just kind of hanging around. It makes our equation a little simpler. We just bring down the ones we don't cross out. And this becomes our net ionic equation. 2 iodides plus the lead gives me lead 2 iodide. Not too bad, right? So those ions we cross out, they're called spectator ions. Those are ones that didn't change during the course of a reaction. So our spectator ions, you can think of them as like spectators in a stadium. They're just kind of watching the reaction happen. They're not actually doing anything for the reaction. Just like how the fans watch the game happen, they're not actually playing the game. The iodide and the lead, those can be thought of as the players for the game. The potassium and the nitrate, they can be thought of as your spectators or fans sitting in the stands. And so to review how we do net ionic equations, first step is you want to balance your molecular equation. You want a correct balanced molecular equation with correct products and write the phase for everything. Writing the phase is important for when we get to the next step. And the next step, we dissociate all the strong aqueous electrolytes, and only the strong aqueous electrolytes. So that means everything on the reactants here, they dissociate. The lead iodide, that stays together because it's solid, it's not aqueous. The potassium nitrate, that dissociates. Then you cross out the spectator ions, cross out the ones that are the exact same on both sides. Once you cross out the ones that are the exact same on both sides, write whatever is left over. That's how you're writing the net ionic equation. This way we can tell what actually is reacting together. And so now you guys should be able to write your net ionic equations as long as you follow these 4 steps. It shouldn't be too bad. The trickiest part will probably be figuring out which ones to dissociate. And for that, just remember, it has to be a strong aqueous electrolyte. Anything that's not strong aqueous electrolyte, don't dissociate it. So I think step 2 is always kind of the trickiest one. Because once you get a good complete ionic equation, it's easy to cross them out.